Hi everyone, in this video we are going to review the Global Climate Change module, or the Global Warming module, whatever you want to call it, we're going to review it. And so how I do reviews is I usually split them into two sections. I have a context section, so that's primarily the facts, or the bare minimum, the information that I provided you throughout the module. They're simply things you just need to memorize and you need to know as much as you possibly can about them. The second component is the chemistry component, and usually students have a more difficult time with this part because that's the actual application. And so for this section, you need to know the information and then be able to use your brain and apply it to a brand new section when we're seeing a problem for the first time. And then at the very end today, we're going to do 3 different problems that I personally think are kind of the most challenging of what you have to do in this module for the exam or on the final exam. And so we're just going to put these forward for you so you have a little bit of extra practice, so some new problems. All right, so let's start off with the easy part. Easier said than done, yes, but the context section. So this is just the bare minimum, the memorization part. All right, the first thing we talked about was the Earth's energy balance, and we have that beautiful diagram, and really 2 beautiful diagrams that if you put them together in one, you can see the total Earth's energy balance, where we're not creating energy, we are not destroying energy, we're just transferring it from the sun to the Earth, and it goes in a number of different places with the Earth's atmosphere, outside of the atmosphere, and the surface, a number of different places. You need to know that diagram. You need to know every single component of it, and make sure you know numbers. You need to know everything you possibly can of this diagram, okay? Know it. All right, after that, we talked about the greenhouse effect. And we know how with the greenhouse effect, usually what we're talking about is how visible light is able to penetrate glass windows. And so it comes in and then it's absorbed in our dark surfaces. It's re-emitted as IR radiation, but IR radiation cannot actually get out. It can't go through those windows or anything else. So the IR radiation is trapped. The same concept happens here in our planet, on our planet. Our greenhouse gases are able to trap that infrared radiation, and it's not able to leave our atmosphere, so it ends up being reflected back down to the Earth. So our greenhouse effect is when about 80% of that energy is absorbed. However, what we're experiencing here on Earth right now in 2015 is we have the enhanced greenhouse effect. And the enhanced greenhouse effect is when you have greater than 80% of that energy absorbed. So this is what's happening right now, and it's not a good thing. It's actually a bad thing, but you need to know both of them, and you need to know the difference. All right, so then we talked about 6 different greenhouse gases. Yes, you need to know all of them, and I expect you to have them in a very particular order. So number 1, when we talk about greenhouse gases, I want carbon dioxide in your brain right away. That should be the first thing you think of. That's the main thing we talked about in this unit. Number 2, or the second worst greenhouse gas, is methane, CH4. That's the second worst. We're going to talk about that big time in the next unit for our combustion unit, but for right now, we know carbon dioxide is worse, methane is the second worst. After that, I don't care how you memorize them. They can just put any 4 however you want to do it, but 1 and 2 have to be carbon dioxide, then methane. That's just the order. So let's just throw these out here. We have N2O. We also have some ozone. We have water, and then we have our CFCs. Now remember, I expect you to still know Freon 11 and Freon 12. Those have to be in your brain this entire semester, so do not forget those. You need to know the structure, you need to know their name, okay? All right, so let's focus more on CO2 because that was the important one, or carbon dioxide. And so when we talked about carbon dioxide, at least in the context section, we really hit 3 different things. The first one was the carbon cycle. So there's 7 different processes. When we burn fossil fuels, it doesn't have an equal but opposite process. So it's really important that you have that whole thing in your brain. So into the ocean, out of the ocean, photosynthesis, respiration, deforestation, reforestation, and so on and so forth. That's your carbon cycle. Then we also talked at the very end about 2 different other types of carbon situations. So the first one is carbon capture and storage. And this is a way where we try to capture our carbon dioxide or carbon monoxide that's emitted from whatever it is that we're talking about, and we try to store it somewhere else, underground, in limestone, maybe underneath a river, something of that sort. But we absolutely need to be familiar with what carbon capture and storage. But that should not be confused with what is called our cap and trade system. And so our cap and trade system, remember, was our alternative. And so what we did is we used this instead of signing different protocols and so on and so forth. We used our cap and trade system so that we did not cripple our economy. And we wanted to make sure that certain companies were able to slowly reduce their emissions without going bankrupt. But basically, it's an economical collaboration between 2 different companies. If you release more emissions than you're allowed, then you need to buy emissions from somebody else. If you release less emissions than you're allowed, then you can actually let somebody buy or kind of gain money by being a green process, okay? So it's a really, really good system. But do not get these three confused. You need to know what they are and make sure you have them very separately in your brain. They are not the same. All right, and then this brings me to the Ipcc. The Ipcc, we talked about this a lot. The first thing is you need to be very, very comfortable with their confidence levels. Okay, what are the confidence levels? Is it likely? Is it very likely? Is it unlikely? You need to know those words. Be very comfortable with them, especially at the extremes. Those are normally what I care about. All right, now we know that the fifth report just came out, so you need to make sure what all those pieces are in the fifth report, especially the ones that I spent a lot of time on and highlighted in previous videos. Also, what we need to talk about, and this is probably the most important thing, is that there are 7 effects of climate change as deemed by the Ipcc. You need to know them. So this is your ocean acidification. It's your loss of biodiversity. It's the fact that your glaciers are melting or that there's more extreme weather, so on and so forth. You need to know all 7. You absolutely need to have those right there in your brain just ready to go. Okay. A lot of these we've actually experienced here in Austin, so hopefully it won't even be that hard for you to memorize. All right, and then we kind of concluded this section by talking about climate models and the laws that we have built to kind of protect our environment. So let's start with climate models. And the first thing we focused on were radiative forcings. So our radiative forcings are basically in 2 different categories. We talked about them from either our anthropogenic or our human sources and our natural sources. So the thing that we need to realize is regardless of the source, human or natural, they're always red. They overall and end up to be red or positive warnings, which are not good because that actually means we're warming our planet. We're not cooling our planet, we're warming our planet overall with both human and natural sources. So be comfortable with that. And then with our climate models, we also came up with some other information, which was primarily the GWP, which is our global warming potential. And you absolutely need to have the big 4 memorized. So the first one is carbon dioxide, and we set that value to be 1. So carbon dioxide has a GWP of 1. That's our relative. We compare everything to that. Now, methane has a value of 21. It's much, much, much worse. It absorbs IR radiation so much better than carbon dioxide does, but we have a smaller concentration of it, so it's not as big of a deal today in 2015. We'll see what happens in the next couple years. We also have N2O, which has a value of 310, and then we have our Freon 12, which is my specific example here, but often our CFCs are around 8,100, so a ludicrously high value for our GWP. Those are the 4 you absolutely must know. There's no other way around it. You just need to memorize those. All right, then we also talked about a couple different laws that were put into place. I expect you to know the 3 U.S. laws, okay, that I highlighted. You absolutely need to know those. There was also a mayor plan. I'm just going to write it as the mayor plan, but hopefully we're all comfortable with that, and we know it's the U.S. Mayor's Climate Protection Agreement. Okay, it's a big, long name, but you need to know what it is. And then we also have one here in Austin that we really like, which is our Austin Community Climate Plan. I'm just going to write out Austin Plan, but basically you need to know about all of these. You need to know what the U.S. did, how we tried to fix our global climate change issue. We need to know what the mayor's plan was, because that one's awesome, where all these mayors came together from across the United States, and we all worked together to try to reduce our carbon dioxide emissions, which is awesome. And then we also have our Austin plan here. All right, so that has it for our context section. Now what I want to do is move on to the chemistry part. Yay, chemistry, the fun part. All right, number 2, chemistry. And again, this is usually the part that's a little bit more challenging just because it has the application sort. So if you can only spend, an hour or whatever studying this, which is not even close to enough time to study, by the way, but if you can only spend an hour, you want to make sure you're spending 45 minutes or so of your time on the chemistry section. That's the important part. This is chemistry and context, so make sure you focus on this section as well. All right, so a lot of this stuff is just you have to be able to do it. You need to be able to determine the atomic mass of something, the molar mass. You need to know what a mole is. You need to know that it's equivalent always to 6.02 times 10 to the 23rd of something, of things, whatever it is that you're talking about. Shoes, penguins, whatever you want to talk about, that's what a mole is. You also need to be able to determine mass ratio and percent. I have a semi-tricky one that we're going to do here together at the very end of this chemistry section. Okay, so don't worry about that. We also have dimensional analysis. So we come back to this. Just cannot get rid of dimensional analysis at all. And so what I expect you to do here in this section is you absolutely need to be able to go from grams to moles to molecules and then to atoms. Usually students struggle here, this section, the molecules to atoms, okay? So focus on that. Find example problems and drill it, drill it, drill it. Do the best you possibly can to get from molecules to atoms. But do not get hung up on this. It's not just grams to moles to molecules to atoms. You absolutely have to be able to go in the opposite direction. So if I give you atoms, like you have X oxygen atoms, you need to be able to tell me how many molecules, how many moles, and absolutely how many grams that would be. So you must be able to go in both directions. Usually people find it more challenging to go this way, so absolutely make sure you spend some time on that. You need to get this skill down. All right, that's our dimensional analysis section. After that, we talked about molecular geometries. So that was a fun section. I really like molecular geometries for some reason, but it's basically just a way to think of what our molecules look like in space. So actually, their 3D arrangement in space. Where are their atoms? How is it all connected? And so here are the things you need to be able to do. First things first, you absolutely need to be able to draw it. If I gave you a piece of paper, I would expect you to be able to draw out methane using three-dimensional geometry. I would expect you to be able to name the form of geometry. So I keep using methane as my example. So if methane is our structure, I would expect you to say, okay, I know for sure that that is a tetrahedral molecule. After that, I would expect you to be able to analyze their bond angles. So that's very, very specific. We're either going to be 180, 120, or 109.5 degrees. Alternatively, if it's not one of those three, the only other option is less than 109.5 or less than 120. I'm not going to ask you 104, 107. I want to know less than or less than. That's it, okay? All right, so after the bond angles, the last thing we did is we used the geometry to determine whether or not something is going to absorb IR radiation. And usually the answer is just if there's 3 atoms or more, it's going to absorb IR somehow. But I need you to be able to analyze that and figure out exactly how that goes. So something like nitrogen, N2, is not going to absorb infrared radiation because there's just 2 molecules and they have the exact same electronegativity value. So it's impossible to distort that electron cloud in such a way so that we can actually absorb that infrared radiation. All right, so then we talked about these actual IR vibrations. IR vibrations, because we know when IR hits a molecule, it forces the molecule, or that bond specifically, to vibrate. Okay, we don't dissociate, we do not rotate, we vibrate when IR hits it. So what you need to be able to do is draw out that electric field. So put in your vectors, okay? And you need to be able to interpret an IR spectrum, or let's just say spectra, if I gave you more than one, and I would expect you to look at something and determine if it was a bend or a stretch. And the easiest way to do that is just by looking at where the peak is on the spectrum. Is it at high energy? If it's high energy, then you're definitely looking at a stretch. If it's something that's low energy, then you're definitely looking at a bend. It takes a lot more energy to do a stretch, so that's just the way you can think about it. All right, so then what we talked about was actual carbon dioxide data, and this is where it got so interesting, because basically after everything that we saw, out of all the graphs, out of all the data, we were able to draw one conclusion, and it was simply as we increase the carbon dioxide in our atmosphere, we definitely see an increase in the overall global temperature. Plain and simple. The more carbon dioxide we have, the higher the temperature. All right, so we looked at 2 things specifically. We looked at CO2 data. Okay, and this was in our ice core samples. We are obsessed with ice core samples when it comes to this topic because we can get a lot of data. Now, in this ice core samples, for CO2 data specifically, this is when we looked at our air bubbles, or our trapped air bubbles, and we were able to actually look at the concentration of carbon dioxide. The second thing we looked at was our ratio, or maybe I should say our temperature data. And so we looked at temperature data, again using ice core samples. But for this one, instead of looking at the air bubbles, what we actually did is we looked at the ratio of our hydrogen to deuterium. Okay? Yes, you need to know those words. You should be able to look at this and immediately call that hydrogen. Look at this and call it deuterium. You need to know those words, and you need to be very, very comfortable with it. I also would be able to explain how we look at these ratios and determine what our temperature is. And the last thing we did, and this was more on campus here, but we learned to check your source. Okay, make sure that what you're quoting is a good thing. So if you're quoting something about climate change and you're referencing Bill Nye, that's probably a really, really, really good source. If you're talking about climate change and you're referencing a big oil company that's telling you, oh, it's no big deal, carbon dioxide doesn't matter, not good. Check your source. Is it valid? Is it a real source? Is it telling you real science? Or as one of my professors here at UT loves to say, smell the bullshit. You need to be able to tell if somebody's lying to you, okay? You need to be able to sniff it out. All right, so I'm done with my review for now. We just have 3 quick problems, so I'm going to let you do this on your own, but I will obviously work these out for you at the end. So let me see if we can get down here. All right. Here is your first one. Take a second and go ahead and work through it, and then I'll show you how to do it at the end. Go. All right, did you get an answer? Hopefully you did, but if you didn't, that's totally okay. Let's work through it together. So this thing this problem I should say, is kind of challenging, and it has to do with the wording right here at the end. It says 48 grams of oxygen atoms. So right away, students look at this and they go, am I doing atoms or am I doing grams? And all you have to do is look at your number. What is your number? Our number is 48 point what? 0.1 what? Is it atoms? No, it's grams. So you're in grams. So on your little conversion thing, you're going from grams to moles to molecules to atoms. You have to figure out where you're at, and you're starting at grams. All right, so we have 48.1 grams of our oxygen atoms. So that's going to start on the top, which means we need to put grams on the bottom. Now we're talking about oxygen atoms. So atoms, singular, one thing. So that we just take the atomic mass of oxygen, which is about 16 grams, for every 1 mole of singular oxygen, monatomic oxygen, not diatomic. This is one of the trickiest parts. You have to identify what we're talking about. All right, so now we're trying to figure out how many moles of calcium carbonate we have. And so what we need to do now is go from a singular oxygen to the molecule itself. So what I see is that in every 1 mole of calcium carbonate, so whenever we have just one section of calcium carbonate or 1 molecule of calcium carbonate, we always have 3 oxygen atoms. So we refer to that as 3 moles of oxygen atoms. So now we're in moles. All you have to do is solve this out, and if you type it in your calculator properly, you should get something like 1.002 moles of calcium carbonate. Did you get it? If not, stop what you're doing right now, ask a teacher, shoot me an email, let's figure this out and figure out where your mistake was made. All right, now, number 2. What's the next question? What is the geometry as SF2? Go. All right, did you get an answer? Hopefully you did, but if you didn't, that's completely fine. So the first thing you need to remember is that nature likes symmetry. So you want to draw out your Lewis structure first, and if you can, make your molecule symmetrical. So sulfur in the center, fluorine's on the outside. Then what you do is you add your valence electrons. So we know fluorine always has 7 valence electrons here, and sulfur has 6. So 1, 2, 3, 4, 5, and 6. Now all you do is you try to connect the dots to create bonds with the lone pairs of electrons. And so we have right here, I shouldn't say lone pairs, with your single electron, so an electron by itself that is not in a lone pair. So what we do here is we make one bond, make another bond. Now you check your octet rule. Check your fluorines first. 1, 2, 3, 4, 5, 6, 7, and 8. Perfect. Fluorine's good. Sulfur, 1, 2, 3, 4, 5, 6, 7, and 8. Perfect. Now fluorine again. 1, 2, 3, 4, 5, 6, 7, 8. Perfect. Completely obeys the octet rule. So what you would do then is redraw your molecule, because what you've drawn above is not really pretty and it doesn't really give you an idea of what the molecular geometry would do. And so hopefully you could look at this and be like, oh my gosh, this has the exact same structure as water. We have 4 regions of electron density, 2 are bonds, 2 are lone pairs. When we have that situation and that combination, it is definitely what's considered a bent molecule. Now, if I asked you, you would then tell me that it has bond angles of less than 109.5 degrees. And then if I really wanted to be mean, or challenging, I should say, I would say, does that absorb IR radiation? And the answer is definitely yes. We have a negative side here on our fluorines, we have a positive side over here. If we were to apply IR radiation, we could definitely get some bending, some stretching. We very, very clearly absorb IR radiation. All right, so now we have one more question after this, so let's see if we can find it. Here we go. What is the mass percent of nitrogen in N2O? Go. All right, did you get an answer? Hopefully you did. If not, don't stress out about it. Let's work through it together. So we're trying to determine the mass percent of nitrogen in N2O. So the first thing we're going to do is come up with an equation. So we would say our mass of our nitrogen divided by the mass of N2O. And then we're talking about mass percent. If we weren't talking about percent, if we were just doing mass ratio, I would be done here and we're perfect. But we're not. We're talking about percent, so we have to multiply that fraction times 100. All right, so then what we do is we put our mass of nitrogen above, which is about 14.01. But you have to account for how many of those atoms you actually have. So what I see here in the problem is that there's 2 nitrogens in our N2O molecule. So we have to multiply our 14 times 2. Then our mass of N2O is about 44 grams per mole. And so you just multiply this together. So you basically have 28 divided by 44. And if you do that properly, you should get something like 63.6%. That's it. You're done. Easy peasy. Hopefully that made sense. If not, please shoot me an email or talk to your teacher about it. I would love to answer these questions. Good luck on your exam. Good luck on the final, and take care of yourself.